Waves is a topic that you really need to be confident with your definitions to start with to succeed in. So this first video we're just going to go through the key concepts and make sure we're confident on all of them. So the first thing we're going to look at is the two fundamental types of wave. The first one, often you'll see sketched as a sine wave. The second one is often seen as lines of varying distances apart, like so. The top one, as we should know, is our transverse wave, and the bottom one is longitudinal. So we need to be really confident in our definitions of these, and the things they look at is the direction of energy transfer and the way in which the wave is vibrating. So with both of these examples, our transverse wave is transferring energy along to the right, as is our longitudinal wave. However, transverse wave, energy is going off to the right, but our vibrations in this example are up and down. So vibrations are perpendicular to our direction of energy transfer. With our longitudinal, our vibrations are going left and right. So we've got vibrations that are parallel to this energy transfer. So that is the key fundamental definition, is the relationship between the energy transfer direction and the directions of vibrations. Transverse waves, most commonly we're looking at electromagnetic. They can also be mechanical waves. Longitudinal, again the fundamental type is mechanical. Mechanical can be both. And the big example of a longitudinal mechanical wave is sound. So let's just have a look at a transverse wave and make sure we can get all our equations, all our key definitions, and use those to derive some equations. So there are 1.5 transverse waves. Key definition number one is our amplitude, which goes from our centre line up to the top, and that's our amplitude. The top of our wave is referred to as a peak. The bottom is referred as a trough. And the other thing we can label is our wavelength. Key thing with a wavelength, it goes from a point on the wave to the exact same point on the next wave. So the example I've drawn is going from peak to peak. You could have done it from trough to the next trough. If you're using the centre, make sure the wave is going in the same direction. So at zero amplitude, our wave is increasing. Here, it's zero, but it's decreasing, so they aren't the same. So you'd have to go from here all the way over to there. The time it takes for one wavelength to pass, we can also call our t, which is our time period. So that's the time for one wave to pass. Key relationship, frequency is just 1 over that time period. So the time for one wave, if we do 1 over it, we get the frequency. The other fundamental calculation we do, wave speed, which is c, is just our frequency multiplied by our wavelength. C equals f lambda. So they are the two fundamental calculations you're expected to do in waves. The other thing we need to be confident on is our phase difference. So what proportion of the wave has passed. So phase difference, which we measure in radians, is 2 pi, because there's 2 pi radians in a full cycle, multiplied by d over lambda. So d is telling you what distance of the wave has passed. So if we have a point O, here and here, so these are the exact same points on consecutive waves. So they would be, by definition, one full wavelength apart. When we need to work out the phase difference, we do it relative to one of these points. So we always start it as if it's the start of a sine wave. So d, if we were picking here, would be that distance, to this point would be that distance, to the end would be that distance there. So your phase difference will give you an answer, and it will be between 0 and 2 pi. If you have an answer of greater than 2 pi, you might, for example, you've gone from here all the way over to there, you've done a full cycle plus a bit more. So when you're doing phase difference, you don't want to be thinking about a cycle and a bit. You would start from this point and work out the phase difference from there. So we just sketch our sine wave as so. We start here, which is 0. Then our phase difference at halfway is pi. Phase difference at the end of the cycle is 2 pi. If we're going for the intermediate sections, quarter of a cycle is pi by 2. 3/4 of the cycle is 3 pi by 2. If you want it in terms of the wavelengths, then 0 is going to be 0 wavelength, pi is half a wavelength, pi over 2 is a quarter of a wavelength, 3 pi over 2, 3/4 of the wavelength, and 2 pi is the full wavelength.